I should say that what I'm presenting is joint work with my former student Tracy Walechowski and my colleague Adrian Nachman. Okay, and so I'd like to start with an introduction to geometric inverse problems. And you see I'm a mathematician. I'm the only person I think who will use the whiteboard. Okay, in geometric inverse problems, the objects of study are Riemannian manifolds. So of some dimension m. If you're not too familiar with geometry, you can always think I'm dealing with a topological ball or a domain in R3, let's say, or in R3 and R2. And it comes equipped with a metric. So what this is, if you're not too familiar with metrics either, you can envisage an embedded surface inside Euclidean space. And there's a natural inner product that we can define at each point. And there's a natural notion of distance where for any 2 points you're forced to move on the hypersurface. Okay, so the distance of any 2 points is the shortest curve that you can draw that lies on a hypersurface. Okay? So manifolds and metrics, they're usually expressed locally in coordinates. So you can define coordinates x1 up to xn. And the metric is encoded by a matrix. It's a positive definite inner product. And it's a matrix, a symmetric matrix, okay, which is positive definite at each point. So it depends on the point you're at. The thing to note is in geometry, you can always express a metric in different coordinates. But we must always think that the underlying object is one and the same. It's different representations, different expressions of the same object. Okay. So let me, this isn't quite working. Okay. So the object of study is manifolds with boundary. And so the inverse problem in question is we should think we have a manifold, let's say a three-dimensional manifold, with a metric. And we are sitting at the boundary of the manifold. And we know what the metric looks like on the boundary. And we gather information about the inside, the metric in the interior, but always measuring at the boundary. And from that, we want to reconstruct to find the metric in the inside. Okay. Maybe I should point to this thing. Okay. So there are two types of questions we can discuss. You can label them pure geometry, right? For example, length of GD6. I'll give examples right now. Or geometric PDE. Okay, so we'll go into that soon. So sound waves, which have been mentioned, are studied. And also electrostatics, although it doesn't look like a geometric PDE at all, enters very natural. It's a very natural question. So I'll take 10 minutes to discuss these things. So the most classical and easy to present question is the boundary rigidity question, which is, suppose you have a Riemannian manifold, and for any 2 points on the boundary, you know, let's say the boundary is convex, you know the distance of the 2 points. Okay? You know their distance, so you have information about the metric inside. Can you find the metric based on that information? Okay? So this problem has a long history. Let me explain, before I speak about results, let me explain that the answer is obviously no in general. And here's an obvious counterexample. So suppose you have a surface like this, a surface inside R3, which consists of a disk and then a thin neck, and then it opens up with a bubble. Okay? So even if for any 2 points on the boundary, you know the distance, right? The distance as measured on the surface, you cannot find the metric. It's obvious. And the reason is that the distance is always the shortest path. Okay? You have this little neck here, closed GD6, and you can very easily convince yourself that the shortest path will never go through this neck. Okay? So you cannot find the metric for the simple reason that if I can draw this other manifold here, which is exactly the same up to the short neck, and then do something completely different, right? Okay? These have the same length data. Okay? For any 2 points of the boundary, the length data is the same, but obviously the metrics are not the same. Okay? So the answer is obviously no, and one can pose two questions. Can one find conditions that when the answer will be yes? Or can we modify the question? Okay, so you can't find the metric everywhere, but can you find it at least somewhere? Okay. This is one very classical question. Let me pose a different question, related but not the same. So suppose you have a manifold, and what you know is the following. For each point on the boundary, and each vector that points inside, you can shoot a geodesic, and you can measure where it came out of the manifold, and the direction in which it came out. So suppose what you know is where the GD came out, okay, the endpoint, and the direction in which it came out. Okay? And suppose also you know the travel time or the length of the GD. Okay? Can you, from that information, find the metric? So this, okay, is not the same question as that. And you could see that it doesn't suffer from the same obvious problem. So even in this weird situation, you could take this point and shoot a geodesic, and it will go up, and then it will come down. Okay? So in some sense, you can gather data even about the bubble. Okay? So these are two classical questions: the boundary rigidity question, the lens rigidity question. The lens rigidity is related to hyperbolic PDE. Maybe I won't say too much about that. Let me give a few answers. So to the first problem, this was an open problem for a long time. It's had progress along the years. So the one I want to mention is recent work in the last 5 years of Gunther, Bestov, and Vashi, where the answer is yes, assuming the manifold is simple. I don't want to give exactly the definition of what that is, but you need the boundary to be convex, and then the simplicity means that the exponential map has no conjugate points when you point into the manifold. In particular, it rules this out, but it rules a lot more out too. Okay? So it's a very strong result, and of course it gives, for example, in metrics of negative curvature, a fall under this assumption always, and so you resolve the problem in a great variety of cases. Okay, and the other one was, we even heard about it from Andras Vasi yesterday. So the answer to the second one for convex boundaries is yes, if you assume that the manifold admits a convex foliation, okay? A foliation by convex surfaces. Surfaces that are always convex with respect to the metric. Okay. Okay, so these are geometric PDE questions. Sorry, pure geometry questions. Let me discuss a little bit about geometric PDE. Okay. So this is an interesting subject because you can pose questions where you really don't think there's any geometry at all, okay? But it turns out that there is. So the one problem which is well known, and it was introduced in the first day, was the question of sound waves. So acoustic waves, for example. So if you have a material that transmits sound, and the speed of sound is not constant, you can send in a sound wave and measure where it comes out, and you know the travel time. And from that, you're trying to reconstruct an image of the speed of sound. I don't want to cover that. I'd like to discuss more electrostatics. Okay? So suppose we have an object, a three-dimensional object. Let's even think of a domain, right? A three-dimensional object in Euclidean space, which conducts electricity. Okay? So the main PDE in electrostatics is that the sum of partial I, sigma of x, partial I again of u, is equal to 0, where u represents the voltage, okay, the electrostatic potential, and sigma represents the conductivity. Okay, so sigma here is a positive function, okay, and u is only defined up to a constant, obviously. So the problem in practice is you have an object whose electrostatic conductivity you do not know, but you can inject current in the boundary and measure voltage, again, at the boundary. And from that, you would like to get the conductivity. We can flip the problem to make it mathematically more classical. So we could say we maintain a voltage at the boundary equals F, and I get to prescribe this. I get to put whatever voltage I want, and we measure the current, J of x, equals sigma of x times gradient of u at the boundary again. Okay, and can I find sigma of x? Okay. Okay, this is the case of isotropic conductivity, so where the conductivity somehow is uniform in all directions. It becomes equivalent to a problem for a Riemannian metric, so the equivalent problem for Laplacian g of u equals 0, with u equals f on the boundary, where g is a Riemannian metric, which is sigma to a certain power, never mind what power it is, times the Euclidean metric. And this is the Laplace-Beltrami operator. Okay, if you don't know what that is, don't worry too much. Okay, it's something that sees the metric. In this particular problem, in this particular inverse problem, what we're aiming to find is one function. okay? One function. And the metrics that the one function corresponds to is of a special form. It's called conformally Euclidean. Okay? It arises from the Euclidean metric by just multiplying by a positive number. Okay. We could pose a more general problem. So this is point A. So there are materials that are non-isotropic. So you could have non-isotropic conductivity. Okay. Where sigma, the conductivity is encoded by a matrix, a 3 by 3 matrix, which is positive definite. Okay? So, and the matrix depends on the point, so it's not constant, it's not the same over all points. And then the PDE that governs the conductivity is partial I sigma of ij partial j of u is equal to 0, where u at the boundary is prescribed by us. Okay? Sum ij goes from 1 up to 3. Okay? So this again translates into a geometric PDE problem. So you can build the Riemannian metric out of sigma. Okay? And the problem becomes, can you find this Riemannian metric, this general Riemannian metric, if you know the Dirichlet-Neumann map, if you know for all voltages what is the conductivity you can measure. Okay? All right, let me mention some results here. So for dimensions 3 and higher, this is this problem has been resolved. Problem alpha has been resolved. So for G being conformally flat, conformally Euclidean, this is a very celebrated result of Gunther Ullmann and Sylvester. The way it's actually done, and this here you can see the manifestation of how conformal flatness is used, is it's transformed to a problem of the usual flat Euclidean Laplacian plus a potential. Okay, and then we know the map, the Dirichlet-Neumann map, from f into normal derivative of f. Okay, and this determines the potential. The potential v. Okay, this problem is transformed into that, and if you can find the potential v, you can find the metric, you can find the conductivity. So the isotropic case has been fully solved in a very celebrated result for dimensions 3 and higher. For dimension 2, this proof does not work, and the case n equals 2 requires substantially different treatment for geometric reasons that are very, very easy to spot, but I won't discuss. And so this was done for 3 and higher by Sylvester and Ullmann, and for n equals 2 by my colleague Adrian Nachman, about 10 years later. Okay. So you can find v, determines v. Okay. Okay. So the problem I want to discuss today is in the in the pure geometry category, and I can state it right now. Okay. So suppose you don't know lengths, right, of GD6. Suppose you know areas of minimal surfaces. Okay. So the picture is, suppose we have the same, a Riemannian metric, a three manifold. Okay, where I'm sitting on the boundary, I know the metric on the boundary. But what I'm allowed to measure is not length of GD6, but areas of minimal surfaces. So what that is suppose for any closed loop I take on the boundary, I can consider all possible surfaces with that boundary and find the one with the least area. This is a very classical problem from the 18th century. Okay? So if the boundary is mean convex, there exists such an object. There exists the surface of least area. And assume that I know the area of that minimal surface for any curve I put at the boundary. Can I then find the metric? Okay. So that's the problem I want to discuss today. Okay. So let me say that in a certain sense, you seem to have a lot more data because there are a lot more surfaces than pairs of points. On the other hand, in some sense, the data you have is of lower quality in a certain sense. So somehow a GD6 gives you more information about the metric than a surface, because the surface could be many places somehow. This spirit will come out in the proof. Okay, so that's the question we want to address. So let me say something about the motivation of this. So the motivation, I don't want to spend a lot of time on this, but it comes from a theory in string theory called the AdS.CFT correspondence. It's a theory that posits a correspondence between a conformal field theory that lives on the boundary and general relativity dynamics, asymptotically AdS dynamics that live on the inside. Okay, and one main tenet of this correspondence is that if you take a loop on the boundary like we have, that corresponds to quantum information somehow, and it's called a Wilson loop. And this quantum information should correspond, the expectation value of the Wilson loop should correspond to precisely a notion of area of surfaces that lie in the inside. Okay? If the surfaces actually have infinite area, you need to define renormalized area of some kind. So, okay. And a main principle of this correspondence is you should, if you know all the quantum information in a region, in particular for all loops that lie in the region, you know all the expectations values of the Wilson loops, that should correspond to reconstructing the bulk somewhere. Okay. So a question is if you know the expectation values of all loops at the boundary, you should be able to find the bulk. Okay. And if you only know a region, the expectation values that lie in a region, you should be able to reconstruct a portion of the bulk. So this is posited in Lorentzian signature. One can study the Riemannian signature just as static spacetimes. Sometimes they reduce the Lorentzian problem to a Riemannian problem. Anyway, this is what motivates our study. Okay? And we have essentially solved this question not with boundaries are at infinity, but at finite distance and in Riemannian signature. And this has generated some attention in the physics community. Okay. I'd like to present the results we can prove. Okay. So let me start by saying that, again, it is obvious that you can't solve the problem in full generality. This is more the analog of the first problem I said, the boundary rigidity problem. So if you have three manifolds that contain a minimal surface, if you envisage that this is an S2, a topological S2, okay, then surfaces of least area will never penetrate beyond this S2. Okay, it's always cheaper to stay outside it than go inside. Okay, so if you have such surfaces, you will not be able to reconstruct beyond them for sure. Since I measured the AdS.CFT, let me measure in the static case, minimal surfaces correspond precisely to black holes. Okay? And that's another object of hot interest somehow, how much you can detect. Can you detect everything up to the black hole? Could you even probe what's happening inside the black hole? So we've had some interactions with physicists, and many of these questions have arisen. Okay, now, so it's obvious you can't solve the problem in full generality. The classes of manifolds that we consider are ones that admit a foliation by minimal surfaces. Okay? If you want to reconstruct the entire metric everywhere, you need to have a foliation by minimal surface that penetrates everywhere. If you want to do local reconstruction, you just need to foliate nearby the boundary. Okay? So foliation is you can start with a point on the boundary and end at another point and just foliate along by curves that start at a point and collapse down to a point. And your assumption is that these can be filled in by a foliation of area minimizing surfaces. You can always fill in by surfaces. The question is, do they deform continuously? So this is the main assumption we're imposing. Okay? Okay. And so I'm going to present, we have a few results. I want to present two. So result number one is, suppose you have a three manifold which admits such a foliation. And suppose you know the areas of all of these leaves, and for each leaf you know all areas of all perturbations of this leaf. So if I take one boundary curve and change it a small little bit, an arbitrarily small amount, there will be a new minimal surface that's filling in the tilted curve, and I need to know that I know the areas of those, only for small perturbations. So I'm not using the area of all possible curves, I'm using one foliation and all small perturbations of that small foliation. Okay, I need to impose an extra assumption that the metric is sufficiently thin or straight. And under that assumption, I can find the metric. I don't want to explain exactly what thin or straight is. I prefer to give you a picture. Okay, thin means somehow what you would imagine it to mean. It would mean that the surfaces are small in diameter somehow. Okay, sufficiently small in diameter relative to the curvature of the manifold. So this is thin. Okay? this also is thin. Okay. These surfaces are fairly small. Straight means this is straight, but this is not straight. It means not bent. It doesn't curve around too much. It doesn't have too much turning. So you could be fat. So this would be a fat manifold, but it would be straight. So in this result, the main assumption is that the thinness times the straightness needs to be sufficiently small. One needs to compensate for the other. You can be fat, but then you need to be very straight. You can be thin, and then you get to be very curved. Okay? And then I can find the metric. That's the result number 1. Okay, result number 2 is we now need to assume that the surface has no minimal surface in the inside. When you assume there's a foliation, that's automatic. That follows automatically by maximum principle. Okay, and now we will not impose either thinness or straightness, nothing. But what we will impose is that you admit minimal foliations from all directions. Okay? So let me not explain it in full rigor what that means. Let me just again draw a picture. So minimal foliations from all directions mean I can start from a point here and I can foliate in this direction and end up somehow at a point that's roughly antipodal. Okay? But I can do that from any direction I want to start. So I can also start from a point here and foliate in that direction. Okay? So for each point where I want to start, I can foliate in all possible directions. Okay? I can give a precise definition, but I don't want to. Okay? So the result is, if you're in that setting, again, if you know the areas of all these surfaces and all their perturbations, then you determine the metric. Okay. So I have maybe 15 minutes. I'd like to present some ideas in the proof. Okay. Okay. So people who are not mathematicians may wish to check out. Okay. So let me start with one thing. You want to reconstruct the metric in a fat-headed analyst way. So that means that you want to somehow choose a canonical coordinate system, okay, and find the metric in that fixed coordinate system. That's called gauge normalization or coordinate normalization. Okay, so the way we do this is as follows. So I start. Let me show you the proof for the theorem 1. So I have my foliation, and the coordinates I want to choose are on each leaf. Okay, there's a parameter t. My leaves start from t equals -1 here and go up to t equals +1 there. Okay? And all intermediate t's correspond to one surface. So I need to define 3 coordinates. My third coordinate will be the one that's constant on each such leaf. So my x3 equals a function t. Okay? If a point P lies on the teeth minimal surface, then the x3 coordinate is t. Okay. I need to define another 2. And the way I'll define the other 2 is that on each leaf, I will choose isothermal coordinates. Okay? Isothermal coordinates means that the metric, so I choose x1, x2, such that on each leaf, y of t, the metric g is a function, is a matrix of this form, e to the 2 phi, e to the 2 phi, 0, and 0. Okay? This is a 2-dimensional result. You can always do this in 2 dimensions. All those of us in geometry know there are many ways to do this. There is not a unique set of isothermal coordinates. Let me just say there is a way to normalize. There's some standard trick with which you can normalize isothermal coordinates, and we use that trick. There's a normalized way to do it. Okay, so the total metric G, is e to the 2 phi, e to the 2 phi, 0, and 0. And then the remaining component, G13, G23, G33. And each of these are functions of the points we're at. Okay? So a general metric has 6 independent components, but you can normalize coordinates. And I normalize coordinates, so I'm down to finding 4 functions. Okay? Each of these is one function. These are the same, so it's actually 4 functions. Okay. So that was step 0. Okay? So I just need to find 4 functions. So it's very difficult to just use the area in itself, right? So you just know the surface in a metric where you don't know the metric, and you know something about the area. So you know something about the integral of the determinant of the metric on that. It's very difficult to use that information directly in any way. So what I instead want to do is look at variations. Okay? Look at the first variation of the area data. So let me draw this picture. I can take any fixed surface I want and take any small perturbation of that surface. I know the area of my original surface, and all the way up to my little small tilt, I know the areas of all the ones in between. Okay? So what I know, okay? So because all the areas of all these one parameter family of surfaces are known, I know the first derivative of the area too. Okay? Okay. So I can hope that that will give me somehow geometric information that's more tractable, more usable. Okay, so in fact it is not. The first variation of area just will teach you. It will tell you the angle at which the minimal surface cuts the boundary. Okay, so that's not very useful. In inverse problems, the challenge is to go deep, to find the metric deep inside. Here you're finding boundary information again. So that's disappointing somehow, right? So, but we will continue, and I will look, instead of the first variation of area, I will look at the second variation of area. Okay, so I know that too. Okay? For any one parameter family of surfaces, I can look at the second variation of area, and that is also known for all variations I want to do. Okay, so those who study GD6 are familiar that the second variation of position, right, the linearization of the GD6 equation, is given by Jacobi fields, which are an ODE. For a minimal surface, there is a very classical analogous equation, which is a PDE. So the new surface, whenever I do a variation, the linearization of position of my new surface, it solves a Jacobi equation, this Jacobi equation, a second order elliptic PDE. The Laplacian is with respect to the metric on the surface, and there's this explicit potential, okay, none of which I know anything about. Okay. So the second variation of area teaches me the, right, so this corresponds to variations of the position. They're solutions of this PDE. And the second variation of area teaches me the Dirichlet-to-Neumann map of that elliptic PDE. Okay? It teaches me the Dirichlet-to-Neumann map of that elliptic PDE. Okay? So that implicitly is global information. It is information that goes inside. Right? The problem is that this is a metric on the surface, so the classical results do not apply. Okay? Particular Nachman's result does not apply. You need to have, Nachman needs to have the flat metric here. Now, I chose isothermal coordinates. So solutions of this PDE transform into a corresponding PDE like this. Right. So just a simple conformal change gives me the flat Laplacian times the weirdest potential you could possibly think of. Okay? So, but I learned solutions of this PDE, flat Laplacian plus this weird potential. Okay? So I can now apply Nachman's result, and I learn what this potential is. Okay? So for this Jacobi equation, I learned the potential. That in itself is completely useless. What is useful is that it teaches me, if I do a variation of the boundary curve, it tells me where the new minimal surface will be relative to the old one. In other words, I know solutions of this PDE. Okay? Okay, so that says, in a nutshell, it says if I knew where the minimal surface was, if I knew the metric on the minimal surface, and then I do a variation of the boundary, I know where the new minimal surface will be relative to the old one. I don't know how much I need to move from the new to the old. Okay. So, okay. So still, I'm trying to find the metric, and I haven't done it. So I could just look at the variation I already started with. Now that I know the Jacobi operator, I could say, all right, let me just move the surface in my background foliation. I just move according to my foliation that I already had. Okay. And that will teach me one component of the metric. It will teach me this, this G upper 3,3. Okay, one component of the inverse of that matrix. I wanted to find 4 functions. I worked hard, I invoked made result, and I found 1. So not too much progress. Okay, all right. So I can look at variations that are just the ones that I started with, the background. Okay, I don't want to tire too much, but I want to give an idea how to find more equations. I'm looking for 4 functions. I have 1 equation. I need another 3. Okay, so let me give you an idea without too many details. the idea is that I could look at tilts of my surface and apply exactly the result I just told you on tilts of my surface. Okay? So I can choose any point I want on my manifold. And because I know the Dirichlet-Neumann map, I can find a variation of my minimal surface that will go through that point. So the varied minimal surface will still go through that point. Okay? But I will introduce a tilt. So the normal vector will turn, and I can choose it to turn in any direction I like. Okay? So the old normal vector would be there. The new one, n prime, will move in any direction I like. So I have coordinates, let's say partial 1 and partial 2. I can find a variation of the surface that will move the normal vector only in the direction of partial 1. I can do this because I know the Dirichlet-Neumann map. Okay, and I can apply the result I did now to this new varied foliation, okay, and find the displacement of this surface to the next one somehow. If I do an infinitesimal variation in this direction, I can find the distance of this to the next one. Doing a linearization, I can get an equation on the component G upper 3, 1. Right? I varied in the direction E1 by doing some linearization. I can find an equation for the G3, 1. But the problem is that if we could stop here, it would be an easy proof. But you can't, because the same point lives on a new surface, and the isothermal coordinates of the new surface depend on the metric that I haven't found yet. So I'm somehow back to square one. So it's equal to a known function for me, plus something that sees how the coordinates change when you change your surface. And that is given by a non-local equation, a non-local expression, which depends on the unknowns. Okay? This is a non-local equation of order -2. Its principal symbol is the Laplacian to the -2. Okay? So it's a very ugly expression, but it exists. Okay, and I can do the same thing for the variation of the D2 direction. Okay, so, but still, I got two new equations. So I had G upper 3, 3, and I have an equation linking the upper G's with the same thing somehow, with the quantities I'm trying to find. So two more equations on my unknowns, one more to go. The one more to go is that I can write the metric in this form, but I've forgotten that I was actually dealing with minimal surfaces. The surfaces I have are actually each minimal. So that gives another PDE. Right? The minimal surface equation is a PDE in itself, and that gives a PDE of this form. Okay? I can translate it into PDE on the conformal factor. Okay? So 4 equations in 4 unknowns. All right. We would like to solve them, and up to now I haven't used thinness or anything like that. Okay? You know, how can you solve a system of 4 equations? You need to solve for G31 here, solve for G32 there, all in terms of phi, and then plug into phi. Plug into the 4th equation and derive uniqueness. This involves solving, right? It involves inverting some linear operators, and it's here that we need either the thinness or this foliation from elsewhere. So the parameter that I call thin or straight is what tells you that this perturbation is small, and you can absorb into the main term. You can invert this system. Okay? It's used in that business. Okay. So that I don't want to give any more details. Let me just mention very, very softly the idea of when you have one manifold and you can foliate from all possible directions, but then you're not thin. You don't need to be thin. You just need to be able to foliate from all directions. And I'm just going to explain it by pictures. Let me go back a little bit to physical questions, and I'll end with some physical question. So that's the theorem 1. And the theorem 2. I have a second colleague who is not in inverse problems at all, but just before we were completing our result, he published a paper which was exactly what we needed for theorem 2. So if you have no minimal surface in the inside, and the boundary is mean convex, they proved, so Hasselhofer and Kitova proved, you can construct a foliation by mean convex surfaces, okay? By mean convex spheres that shrink down to a point. Okay? If your boundary is mean convex and there's no minimal surface in the inside, you can construct a foliation by mean convex spheres that shrink down to a point. So that somehow is a frame of reference for us. Okay, and then the proof is not, the idea of how to apply the proof is not too different from what Ullmann and Vashi did. So then I can say that for each leaf, for each mean convex foliation, I can start foliating from the boundary until I touch at a first point. So suppose I've proved that I've reconstructed my metric up to the red portion. I want to push a little bit in. If these are mean convex, I can construct a minimal foliation that goes and touches at a first point, and then I'm going to pursue a little bit deeper inwards from this first point, only for a short time. Okay. The region where I'm trying to reconstruct is actually small. Okay? The region where I'm pushing in, the new region, is actually small by very elementary geometry. Okay? So I can extend from each given point. I can find a foliation that touches for a first time at that point, then push a little bit inward. Okay? And apply the analysis, the ugly analysis that I described. Okay? That's one. Somehow the idea of how you do that result. Okay? And let me end maybe with go back to the physical motivation. So this is an aside, and it's not the main result we have, but a question is very, very big picture. Rather than reconstructing a metric from knowledge of area, which is ugly and technical and so on, sometimes you want to have soft information. So for example, if I have area data at the boundary, can I detect if there's a black hole inside? Just sitting at the boundary, and if I know area data, can I see if there's a black hole on the inside? Okay, a black hole in this configuration is precisely a minimal surface inside the manifold. Okay? So you can prove by very soft geometry, by almost nothing actually, that if you consider a foliation of the boundary, and if there's a closed minimal surface on the inside, there couldn't be a minimal foliation that goes all the way. There have to be jumps. Okay? So you have to find an area minimizer, and at some point the next area minimizer has jumped. Has jumped on the other side of the enclosed minimal surface. Okay. Can you detect from the area data that there are such jumps? Do the area data that I measure see that you actually jumped across? And the answer is you can. Okay? It's actually very simple. If you think of the function of area, it starts from 0 and it goes to 0. If it's a C1 function, there was no jump. If it's a Lipschitz function, right? If it's Lipschitz but not C1, then there was a jump. So an aside of all this is that you can detect soft information about the inside. You don't need to find the metric, right? But just soft information. For example, is there a minimal surface inside? By just studying the regularity of the area function for foliation of the boundary.